Hello, I'm Michael Moggridge from Manvman. Manvman are an Icelandic renewable energy consultant stroke engineering consultant. Give you a little bit of a flavour of what we do. We've got international geothermal expertise. We were the lead designer on some of the largest plants in the world, in Iceland and also abroad. We've been going for over 50 years now, and we have around about 100 employees who have a shareholding in the company. Makes decisions incredibly difficult. Okay, so ground sources of heat. This is my area that I'm going to be discussing today. I'll talk very briefly about deep geothermal CHP. We don't really have that, or sorry Robin, we do have that capability to some degree in Cornwall. Direct geothermal heat as well. Horizontal arrays, vertical boreholes, energy piles, open loop systems. I'm not going to dwell on pond loop systems. There's a kind fellow, Phil Jones at the back, who's going to tell us all about how he loves heat pumps so much. He's going to talk about water sources of heat. And I will talk very briefly, not as much as the guy who was going to talk. I'm going to talk very briefly about the ability of the ground to do energy storage. Okay, so geology. The acceptable face of geology is this fella here, Professor Ian Stewart. This is what most people expect them to look like: a beard, a hammer, a hat, bedrazzled, next to a bunch of rocks. Professor Ian Stewart has taken our industry completely forward, and we're all good looking now. Okay, so clearly the evidence is before you. So geology, what does it look like? Majority of the people in the room, Andy, Ian, Robin as well at the back. Most of you think this is what it looks like. You've got a dinosaur down there, you've got some soil, you've got a few fish bones. You know, that must be what it looks like. In reality, very different. Not too far different, but yeah, it is different. So I'm a geologist myself, so it's one of those things that is key for the ground source heat pump side, is looking at the geology. Now, people will tell you the geology in the UK is the most diverse in the world, and it is. We have pretty much every age of the geological succession in existence in the UK. It can get very complicated. However, this here is a map of London. Every single dot here represents a borehole that's been drilled at some point and is held by the BGS on archive. This is actually an online resource anybody can log into. It's not something special that I only have access to. Anybody can look at it. What I would say is interpreting it is slightly different. It's a slightly more complicated kind of kettle of fish, but broadly there is excellent resource of knowledge on the geology in the UK. Okay. When we look at geology, there's several parts. Effectively, we have drift, superficial deposits, what you probably think of soils. Actually, sands, gravels, clays, made ground where people have built. Typically, or pretty much exclusively, that's unconsolidated. So if you dig into it, it'll want to fall down at some point. Then we have solid geology, which is the bedrock geology, the stuff that lies at depth, the stuff that we drill into. It's not always consolidated. It's undergone something called diagenesis, which is effectively taking, for example, sands and turning it into sandstone. So it's lithified, it's turned into a rock. We then have another section of geology called structure. That's where over time, beds, typically from a sedimentary perspective, there's lots of sedimentary igneous metamorphic rocks. It's essentially with sedimentary rocks, they're all deposited broadly horizontally when they first get deposited, and then over time the earth tilts, well not the earth but the ground tilts, it gets compressed, starts to fold, and you also get faults, which is natural breakages in the ground. Okay, then another area you need to consider when you look at ground source heat pump is mining. Essentially it's the man-made impact on the ground effectively, and the considerations going forward. So for example, there's a chap from the Coal Authority at the back there. Hello. If you want to talk to him about doing anything in a coal mining area, have a chat with him. Basically, whilst you may drill into the ground and there's no coal workings there at the moment, unlikely as it may be, but somebody might want to mine that at a later date. So you have to talk to the Coal Authority and make sure that what you're doing doesn't impact on their resource. Is that correct? That's right. There we go. Bloody hell. I have learnt something. Okay. Topography. Now, I've done this in a slightly kind of jokey way. Essentially, when topography is ground levels, hills, and things like that. Essentially, when you look at the geology on the top of a hill, it can be very different to what's down in the valley. Okay, it can be incredibly difficult. So when you look at these boreholes, all these little dots, if you've got one on top of a hill and your site is down in a valley, it will be totally different. Geology changes as well. All these boundaries here, you know, this effectively, these are superficial deposits. In London, it's fairly straightforward, to be fair. But effectively, you can get different types of geology. So this borehole here will have encountered different ground conditions and geology than this borehole over here. Okay, so you need to be mindful of where you are from a point of view of elevation and how the geology pulls together with it. So whilst this is a great resource, and I'm not saying don't look at it. I'm not saying, you know, I'm the only person who has access to it. You need to look at it with your eyes open. Okay. Hydrogeology, that's where we look at the interaction of groundwater. Essentially, what you'll find is everybody talks about groundwater as there is a lake beneath London. It's nothing like that. What you have is you have rock that has natural space in it, and some of that rock will allow the water to flow through and some won't. Okay, so hydrogeology is all about the groundwater side. So when you're looking at open loop systems where you drill boreholes for water, take the water out of one, put it through a heat exchanger, put it down to in another one, essentially that's where you really need to understand the hydrogeology of the system. Information sources, as I said, there is absolutely shed loads of online information. You can even go to the Coal Authority, look at their records. They're very helpful in that respect. Charge you a bit for it though, but they do help. Geological maps, you know, the UK has been mapped for hundreds of years. Okay, deep geothermal CHP, this is going to be the shortest slide. Basically, this is one of our, if you've ever been to Reykjavik Airport 3 or 4 years ago, you'd have seen this guy smiling at you. This is a geothermal muffler. Those in the room who understand about thermal response tests on the smaller scale, this is what we do on deep geothermal projects. So you've got several tens of megawatts of energy going up through that chimney, and we see the longevity of the system using that. There are some geothermal or CHP opportunities in the UK, but they are limited. Okay, this is deep geothermal direct heat. This is just a very simple kind of model that we have. GTN are one of the companies we own in Germany. They've done some pretty decent systems over there. Basically, you have thermal water inlet, so it comes in through the heat exchanger and then it goes back out of the system. And then we feed into a district heating system, and you have a peak load and emergency boilers when the system needs amending or the pumps need to be changed. Okay, so very, you know, about as simple as it gets. You know, this is no different. You know, it's a heat source. You know, yes, it is technical to work it out and manage it, but it's just a heat source. Deep geothermal with a heat pump augmentation. Effectively, this was a system we looked at up in the northeast of the UK. What we have here is we've got our geothermal wells, abstraction and rejection. What we had broadly was about a 55-degree temperature. Now, 55 degrees for district heating purposes, you know, yes, on very modern housing estates where everything's got underfloor, you could probably get away with it. But in a retrofit example, it's never really going to happen. So what we did was we looked at the ability to use a heat pump to effectively take that 55 degrees, ramp it up to a useful 75 degrees that you could just about get away with in a heat network. Now, with a typical kind of light system, as we showed here, what you would do is you'd have, say, 80 degrees coming in, which you can find in a lot of places, even in the UK, to be honest. You get 80 degrees coming in, and then you have a 30-degree DT on your heat network, and you discharge back down at 50. What we decided here was the best way to get the maximum out of the wells is we had 55 degrees at depth that we were going to be abstracting, and then using the heat pump, we dropped that temperature down to 15. We dropped that temperature down to 15 degrees, so we had a 40-degree delta T, and we ramped it up to a useful temperature. So we had a great resource. It was around about 6 megawatts in this particular case, and then that fed into a heat network that would be able to feed into typical people's homes. Yes, we did have a gas boiler. I think every system has to have a backup that's of this nature, to be absolutely honest. But let's be honest, gas boilers are cheap as chips. It's not like they're really expensive. Okay. So this is just a slide to talk about what the ground is to us. the way we view it, if you like. Essentially, it's your energy store, your fuel tank, your battery, or whatever you want to call it. But you can keep taking from it, but the temperature will drop. Okay, it will go down. Whilst we're a geothermal engineering company, one thing we totally understand is the huge proportion, and it's kind of like well over 99% of thermal input is solar input onto your ground array. And from a heat pump perspective, we're not talking about drilling into volcanoes in this country, really. What you're talking about is solar thermal top-up through the year. Okay, so if you just take the heat from the ground, you're relying on solar energy to basically warm your temperatures back up when you don't have a heating, or when you're not heating effectively. As I said, very minor geothermal input. The ground itself is relatively stable. It's not going to change that much once you've drilled your boreholes. The one thing I would say is you do get groundwater flow across the site. In some sites it's nothing at all because the groundwater's at depth. In other sites it's not very much at all again because it's clays or it's very low permeability rocks. On other sites where you may have pumping stations nearby, you can have very significant amounts of groundwater flow across your ground loop. Okay? And when you've got closed loop systems, that can either help or hinder. I generally think it's a good thing to have a nice fresh amount of energy coming in, but if you're trying to do energy storage at any scale, ideally you don't want all that energy that you've stored to go away again. One thing I would say is pretty much it's always best to try and have a system that's either heating or cooling, or you're replacing what you've taken out, because then you don't have to have such a big ground array. The thermal output of your system is about the size of your tank, and if you keep topping it up every year through the summer or whatever that means is, you can reduce the size of your tank because you're not always taking from it. Whilst it's the best thing to do, it's not completely necessary. You just have a higher capital cost to install your ground loop. One thing I would say about ground source heat pumps and systems like this, your energy storage is on a seasonal scale and beyond. So effectively what you're doing is you're taking heat out of the building during the summer and replacing that, or putting it in the ground in the summer and taking it out in the winter. Okay, so it's seasonal storage. Okay, so that's one of the biggest benefits to my mind of ground source heat pumps, is the ability to run them when you need, not when it's warm enough outside or when it's absolutely freezing cold. You can run it exactly when you need it to run. Okay, so the important points of what we do and what we need to know. You should always start with, and depends who you talk to, but Andy, would you agree? Always start with the building. Absolutely, Andy Howley from Ground Source Consult. Thermal demand of the building, the heating and cooling side of it, because there's no point trying to design a ground array when you don't know what you're designing for. Okay. Then you need to look at the thermal characteristics of the ground. These are the basic points. You need to understand the thermal conductivity. That's how well the energy flows to or flows away from the well. All right, it's nothing overly complicated. These systems aren't really difficult. Temperature, it depends very much on what the ambient air temperature is, but you need to know what the ground temperature is. So, for example, in London, you're typically looking at somewhere between 12 and 15 degrees as your starting temperature at near surface, because effectively London is a heat island. If you go up to Aberdeen, you're talking about 7 or 8 degrees because it's a lot colder up there. You also need to know the specific heat capacity of the ground. That effectively is saying for this chunk of rock, a known volume, this is how much energy it takes to change that volume of ground by 1 degree Celsius. Okay, because what we're doing is we're cooling the ground. So we're making that warmth come towards the borehole, or making the heat go away from the borehole in cooling mode. And with all this information, what we're trying to find is the optimum way to couple with the ground. Okay, typically if we're looking at very large kind of heating only projects, what we would suggest is when you go beyond a few hundred kilowatts, it's probably better to look at open loop systems where you're drilling groundwater wells and you're abstracting from one side of a site, and a few hundred meters away you're discharging to the other side of the site. That way you're just getting nice, fresh, relatively warm 10, 12 degree water coming to you all the time. If you have it too close together, if your site's very small, what you'll find is you'll get thermal interaction between the wells. So the water you've taken out at 10 degrees and dropped it down, let's just say for a number 5 degrees, as it comes back at you, it won't have warmed up in time, and you get what's called thermal breakthrough, and your system will degrade over time. Okay, so on open loop systems, whilst the thermal conductivity and the temperature and the specific heat capacity is important, we also need to understand what's the sustainable yield from that borehole. How much water can we take and recharge into the ground over the long term, over the 20-year period, okay? What I would say is there's an awful lot of science around this, and there's an awful lot of water wells that have been looked at and monitored. This can be calculated. Open loop systems are very much more complicated than closed loop systems, okay? But there is an awful lot of knowledge around in the industry to look at that properly and understand the sustainability of it. And then in small letters, because everyone runs a mile when you hear this word, artesian, that's where water comes at you without the need of a pump. Whilst it can be to your favour when you're just looking to take water out of the ground, if you're not expecting it and you're not set up for it, it just keeps coming, and you've got a hole that's just sat there, just blowing 20 litres a second. Ian and Andy drilled an absolute beauty, several hundred litres a second. However, they knew it was coming. They planned for it. The system was designed for it, and it works incredibly well, I would imagine. It's a great system. So provided you're planned for it, it's not an issue. You just need to be prepared. Okay? A few more important points. I'm not Harry Potter. This is not the dark arts. This is science, okay? Ian Stewart said it himself at the start. I don't know if you saw him. It's fairly, these systems are fairly straightforward to design. We're talking about a fuel tank, and we're taking energy from it and we're putting it back in. Yes, you can design them terribly. There's some shocking examples out there, but provided you just use some fairly simple principles of engineering, they actually work brilliantly well. Gas boilers, wood, biomass, anything you want to look at, if it's not well designed, it is not going to work, okay? So it's not just a fault of heat pumps, it's a fault of anything. If it's not well designed, it's not going to work. Okay, so just very, very quick few examples. This is from a website that I nicked today when I was making my presentation. Idaho Geothermal. I'll just give them a little bit of a hello. I don't know who they are. I've never met them. Basically, this is a closed loop system, horizontal. These are what we call slinky tubes, and effectively this looks quite sandy. And in all honesty, if it is quite sandy, it's not going to work very well because the conductivity of dry sand is shit. It depends what they put in. You're exactly right. Anyway, so this is basically a horizontal system. Very cheap to install. You don't need expensive drilling rigs. Sorry, Gary. Very straightforward. Okay. This is quite a large house by the looks of it. It's quite a large array. Okay. Then we have closed loop systems. These are vertical closed loop boreholes. It's very similar to those slinkies, except they're straight and they go directly straight down. Okay, they go straight into the ground. Now, what I would say with these systems, and we're looking at a few, they don't have to be outside the building. You can actually drill them inside the footprint of the building. So in London, all you London consultants who are looking for these projects and thinking, how do I get this in mine? You don't have to drill it on the outside of the building. You can drill it in the footprint of the building before the building goes up. You don't need to come back into these closed loop systems, well, hopefully ever again. As long as you keep them leak free, as long as they're well installed and they're not blocked, they'll work for years and years and years. Okay? The plastic you use itself is HDPE, PE 100 plus virgin grade, blah blah blah. Andy used to say, how long does it last? Hundreds, nearly as old as you. Okay, so it basically lasts for well in excess of the life of the building, I would suggest. Okay, now this is my talk about energy storage and how you can integrate all these lovely systems. And what I would say is when we talk about thermal top-up of the ground, we're not just thinking about cooling of the building. I honestly don't mind where the heat comes from. If I'm heating a building there, or whatever it is, heating something, I'm cooling the ground down, I just want to replenish that energy I've taken out. It makes my borehole array much smaller, it's much cheaper from a capital perspective. This, and I will do my very best because this is, I've only seen this from Thursday. This is GTN, Geothermal Neubrandenburg, who's a German company, part of the Manvman group. They designed and essentially the Reichstag over in Germany, the heating and cooling system. What it has is it has multiple parts to it. Effectively, we have... Is there anybody really good at German in the audience? What we have here, Thomas? Warmspeicher. Wärmespeicher is the heat storage. So at 300 meters deep, okay, so I'll try my best. At 300 meters deep, we've got a warm store. So what we do is we put all of the heat effectively from the buildings. When we're in cooling mode, we're taking heat out of the building. We put it down at 300 meters. And when we want to warm the building, we can take it back out, okay? Well, we also have these, I believe, are the energy piles over here, these blue effects. These are our cool stores. So what we do when we basically put cool into those, and effectively have that as our cold store for the system, and that helps basically keep the building cool during the summer months, etc. And then we also have the Stromleitung, which I believe is electric mains. We also have, I think there is a CHP unit in here somewhere, because we take the waste CHP, or the waste CHP heat, the stuff from the intercooler, and we also store that into the warm store at 300 meters down. Okay, so what we're doing is we're just harvesting as much warmth from the building wherever it's coming from, whatever waste heat we have. We basically take that and we store it into the ground. Okay, and we reuse it when we want it. So the funny thing about buildings, and you know, I'm coming out of the ground and into the building, and there are other people who are talking about that. Buildings are funny things. It's not just a seasonal thing. You don't have a heating season only and a cooling season only. It's not even a daily thing where you have one day you need heat and the other day you need cooling. What you'll find is in the morning, first thing in the morning when the sun comes up, one side of the building will start getting warm, really warm, and you'll probably need cooling load in the shoulder months in March and April. But the other side of the building's still cold, so you'll need heat. So there's an awful lot you can do, and there's someone else talking about above ground thermal shifting. But I would say on a seasonal basis, there's not many technologies that work as well as the ground to act as your seasonal store. I believe that's it, and I think am I-ish on time? There we go. Thanks very much.